Okay, I'm all set. So, first of all, I should say I'm extremely happy to be here. It wasn't clear I was going to be able to come, but I was able to come, and I'm very happy it worked out. So I'm the leader of the California and the Western U.S. fan club for Boris. As my role as the leader, I'm here to wish you happy birthday. So actually, I'll say this before starting because otherwise it'll go too long and I'll run out of time and I don't want to. So of course, I became interested in optimization right around when I was starting my PhD, and I read many things actually by people in this room. At a time in translation, I read, of course. But I read these things at a time when actually many of the people here, but especially Boris, were just abstract concepts. It was just a name, at the top of a paper, and it never occurred to me I would ever actually meet these people, let alone come to know them and be friends. And so it has had an unbelievable impact on me. I know you know that. Huge. You don't even know how much of an impact it has had, but it's been very huge in every way, both the content, but also the clarity and the simplicity and beauty of the writing. So anyway, all right. So today I'm going to talk about domain-specific languages for convex optimization. And this is stuff that's been going on for a while, but this is just another description of it. And it's the basis behind things like CVX. But then there's new versions of this, like CVXPY. This is a Python version, and there's a Julia version. These kinds of things. It turns out in real languages, that would not include MATLAB, I might add. In real languages, you can write the core of these systems in 50 lines. And so, in fact, I'm going to tell you today exactly how to do it. In fact, it's embarrassingly short. So, okay. So what I'll do first is talk about, very quickly, because I think people here know a lot of these things, I'll talk about constructive convex analysis, cone representations. I mean, this was developed by Arkady and Yuri. I'll talk about how canonicalization is, and actually, embarrassingly, this is going to be one slide. And it tells you exactly how things like CVX works. It's just one slide. And actually, in a real language, the code is not more than 50 lines for the core. Okay, so the question is, how do you solve a convex optimization problem, right? So, I mean, the best way by far is to use someone else's solver, right? You go to Google and you type in LP or QP or whatever, and you get some code and you use it, right? And that's the idea. Now, of course, the problem has to be in a standard form. Now, the advantage of this, at least in society, is very, very simple. It means that there's people who can devote their lives to making solvers, and then there's people who can just devote their lives to taking problems and mapping them into a form compatible for a solver, right? So it actually makes a lot of sense. It means if you work on linear programming, for example, any advance that you make will be shared by, tens of thousands of people solving linear programs in 50 different fields, okay? So this makes sense. Okay. Now, of course, you can always write your own solver, right? That's a lot of work, but if you do this, you can actually get a lot of advantages. So this is good. Now, there's another interesting way to extend the reach of a standard solver is you can transform your problem into a standard form, right? So you can take your optimization problem and then transform it to an equivalent optimization problem where you know ahead of time that when you solve that problem, you'll actually can extract a solution of your original problem, and then use a standard solver, right? And so that extends the reach of things like LP and QP. And these things, everyone knows about these things. This would be like, doing L1 minimization. And everyone knows you can write that like as a linear program, okay? So of course, when in the classical way to learn about these things, these are just a set of tricks. And you apply this trick or that trick or this trick. And people learn these things, right? But in this talk, what I'm going to talk about is how do you make this completely automated? And in fact, there's a very simple way to do this. And it's very close to the math, too. So I'll show you what that is. OK. So question is, how do you tell if a problem is convex, right? So, I mean, well, you can use the basic definition, right? You can compute the Hessian if it's differentiable and check if it's positive semi-definite. This is, except for extremely simple cases, this is a complete waste of time. I mean, it's just not going to work, right? Or it'll be too complicated. So a more effective method in practice is via convex calculus. So what you do is that you'll have a catalog of functions that you know are convex, right? And then you'll have a set of rules that preserve convexity, right? So this is the idea. And you'll combine these and you'll create things and that sort of stuff. Okay, so this is the idea. So basic examples, I mean, I won't go over this because I think everyone here knows all these things, but you know, you have your obvious things. You have power functions, exponential, entropy, you know, quadratic functions, norms. The maximum of a bunch of things is a convex function. And then you'd have less basic examples, right? The simplest example, as far as I know, that most people don't know is convex. I mean, I think people here know, but it turns out if you just the first problem that people don't know is generally something like this. It's just x squared over y. It's a very, very simple function. Log sum exp, things like the log of a CDF of a Gaussian would be log concave. Log determinant of the inverse of a positive definite matrix, various things like this, or the sum of the largest k entries of a vector. That's a function which is piecewise linear and it's convex. Okay, so these are all just examples of things that are not these are not obvious, whereas you know these are just sort of immediate, right? Okay, and what are the rules? Well, when you teach people, you would teach the rules kind of in order. You'd start with the obvious ones, and you'd say things like, oh, you know what? If you have a convex function, twice the convex function is convex, right? So, okay, sure. That's obvious. You have the sum of two convex functions is convex, right? If you precompose a convex function with an affine function, this thing is convex. Okay, these are all have like 2-line, 1-line, you know, verifications. Pointwise maximum, right? So if you have pointwise maximum, this function is going to be convex. Again, these are very easy to show. Partial minimization. So if I have a function of two variables and it's jointly convex in both, then if I minimize over one, what's remaining is convex. And then you have things like a composition. So a convex increasing function of a convex function is convex. Okay, so and then with these rules, you put them together with these atoms, right? These things, and all of a sudden you can actually show a lot of things are convex. Okay, so it turns out when you teach, I mean, this is how you explain it, right? But it turns out, in fact, all of these go down to one rule. There's in fact only one rule, and it's extremely simple. It's this. It says that if you have a function, a convex function of k arguments, that's convex when the outer function is convex, and for each I, either this function here is affine, in which case it has nothing to do, or this thing is convex, in which case h has to be increasing in that argument or decreasing if that's concave. Okay, so that's the one rule. And in fact, this rule subsumes all the others, right? So, I mean, it's not a great rule for human beings because human beings like to think this way, right? But I mean, for example, let's take this one, pointwise maximum. So, or let's even do this one. How about non-negative scaling? So you take the function to show that this is that. It's very simple. You take h is just, you multiply by alpha, right? And so it's a linear function. It's convex. It's increasing. And so it matches this, this rule matches this first rule right here, right? The max. So the max works because the max function itself is convex, number one, and number two, it's increasing in each argument. By increasing, I mean non-decreasing, right? So it's increasing in each argument, and so it matches, right? So the point is that all of these rules that you might teach to a person, or you might imagine if you were writing a code to do this automatically, all these rules, you can imagine cases with, you know, oh, if it's a sum of things, do this. If it's the max of things, do that. This is all nonsense. What you need is exactly one rule, which is this, because in fact, that's how you write software that actually works. This is correct. It has to be extremely short and close to the mathematics, because there's no other way to get it right. It's impossible, right? So, okay. So that's the idea. So there is in fact just one rule. There's not even multiple rules. There's only one in constructive convex analysis. Okay. So the idea is we're going to do constructive convexity verification, and you start with a function, but it's giving as an expression. So I give you an expression, so it's formed from this library of basic functions, and then operations that you do on it, right, and compositions. And you build the parse tree for the expression, so you understand exactly what the tree is. And then what you do is the leaves are going to be variables or constants and parameters, and then the nodes are functions, and they're functions of the children in this tree. And each one has to match this general rule. So then what you do is you simply walk the tree, and what you do is you tag each expression as either convex, concave, affine, or constant. In fact, even this is too complicated. This is, again, for human beings. The code is much simpler, because affine is when you're both convex and concave. So in fact, you just mark it as convex and concave. So it's even simpler, the real thing. And that's the idea. And you can do things like, if you want, you can actually tag the sub-expressions for signs and then use sign-dependent monotonicity. So for example, the square is, of course, not decreasing. But if you knew that the argument was non-negative, then, of course, it's increasing, right? And, of course, what you get is a sufficient but not necessary condition for convexity. Now, it turns out, does this... Then remember, and the important point to remember is that this is not for detecting convexity. That's a different problem, and actually it's an irrelevant problem. It has nothing to do with actually practical use of these methods, right? What you want is a good method for easily determining and making it completely obvious whether something is a convex problem or not. And for that, you use these methods. Okay. So we do a quick example. So here's a function. I have two variables, x and y. The max has to be less than 1, and here's my expression. Okay, so that's convex. And the argument would go like this. You'd look at the leaves, and the leaves are the basic arguments, right? So there's x, y, and 1 are the leaves, if you can visualize the tree. I'll show you the tree in a minute. And then what you do is we'll go from the middle, from the bottom of the tree up. So you would say, oh, look, x minus y, that's an affine expression. And then you'd see max of xy, that's at the bottom of the tree, that's going to be convex. At the next level, you would have this, you'd have a minus, and the arguments are 1 and max, and you would know that the difference of 1 minus convex is going to be concave. By the way, that's the way I say it to human beings. The way you actually do it is unbelievably simple. You have the function, 2-argument, which is subtraction, and it's convex. It's affine. I mean, that's stupid. It's convex, right? And it's decreasing in the second argument. So it matches the first. It matches that one rule is matched, right? So, okay. And you go through, and then finally you get to the top level, and the top level is the function which is the square divided by a denominator, right? And you know that that's convex. This argument, the first argument here, is actually affine, so nothing to check. And the second argument here, this thing is decreasing in V, and so this thing has to be concave, and it is. So done. There we go. So this is, I mean, it's just a simple example. So here's an example. Oh, actually, so this is fun. This was an undergraduate put together a very, very simple thing that actually just interactively parses expressions like this. It draws the expression tree like this. And this is actually that example. And so you probably can't see the details if you're back too far. But this would be the original function. And what it is on the right is flagged the sign of everything. And then on the left is flagged the curvature, right? So for example, 1 is a constant. X is, well, it's a linear. It's affine, so that's that symbol. And you simply walk up the tree here like this. Actually, so this is actually running live and used for lots of things. So it's this. You should go look at it. It should work even on your phone if you want to try it. And in fact, we made something that was fun, which is we actually have a quiz mode. So it'll generate random expressions, and then you have to check if it's convex, concave, or neither, or something like that. So okay. So disciplined convex programming. This is just a framework. Is how do you describe convex optimization problem? The idea is it's based on this constructive convex analysis. So the idea is, and these things, of course, are sufficient but not necessary for convexity. And there's no apology made there. That's the intention. This is what it's supposed to be, right? And this is the basis for a bunch of domain-specific languages and tools for this, right? So, so this is actually this is in fact the formal definition right? So if you know about things like Backus-Naur form for describing a language, this is actually it. I mean, it's extremely close. In fact, this is even too long-winded. This is for a human being, but here it is. It's something, it's got 0, 1 objective, and it can either be minimized, it's either minimize a convex expression or maximize a concave expression. And you have constraints that are either affine equals affine, concave bigger than convex, or convex less than or equal to concave, right? So, by the way, what this means is that the fact that you can formally define the language like this means that in a modern language, like Python, Julia, any of these, in any real modern language, Ruby, it means that I can write 15 lines of code and I'll get everything for free. Everything will be implemented and it'll be implemented correctly and perfectly, right? So you don't have to sit there and imagine writing all sorts of cases, everything, because you'll never, number one, you'll never get that right? And there's also, number two, there's no point to it, right? So, okay. So expressions are formed from variables, constants and parameters, and functions from a library, right? And then for a library function, the only thing you have to implement, there's one more thing you have to implement, we'll talk about that in a minute, is you have to know the convexity, the monotonicity, and the sign properties, right? And then it's actually, everything else comes for free. The parsing, the analysis, everything else. Okay. So DCP, the idea is that a disciplined convex program, it's convex by construction, right? So the idea is not that you type in what you want and then check if it's convex. You build it following an incredibly simple rule list, and then it will be convex, right? And the right way to say it is it's syntactically convex. So it understands absolutely nothing. The only attributes of the atoms that are used, the only attribute is curvature, monotonicity, and sign, which is actually, think about it, it's the sign of the 0th, 1st, and 2nd derivatives. That's it. So it's doing the most elementary, basically, sign arithmetic, right? But with 3 derivatives. Well, 0th, 1st, and 2nd, right? And that means, for example, that the signature for square root and 4th root are identical, right? They're positive, they're increasing, they're concave, and everything that will work for one will work for the other, which tells you, of course, that, anyway, so that's the idea. Okay. So I'll tell you a little bit about cone representation. Of course, that's developed by Yuri and Arkady, right? So a cone representation of a function is this. You write it as the optimal value of a cone program where you only optimize over some of the variables, right? So you write a function f of x as you minimize an affine function, subject to linear equality constraints and a cone constraint, but you're only minimizing here over y. And the optimal value as a function of y is the function, right? So we'll get to this in a minute. So it turns out, this is the only thing you use in a DCP system, right? So there are no gradients, there's no subgradients, there's no proximal operators, there's nothing. There's just this, right? And so that's the idea. You take this. Again, this is 20 years old from. Okay, and examples, people have seen this, so I think I'll go quickly. But for example, you would write the square root, the negative geometric mean. You'd write it as a little semi-definite program like this, right? For example. If you wanted to write, here's a function which is the sum of the k largest entries of a vector. It's convex, and it's increasing. And it's just this. It's the optimal value of a linear program. These things are not hard to show. But this is actually this is how you define a function, right? So there's no, again, it's a higher level, the description of the function is actually through its graph representation, not through gradients, values, and all that kind of stuff. Okay. Now there's lots of these. Some of these, there's even a few that I think Yuri doesn't know. I would consider those just to be, if Yuri doesn't know, no one knows, right? But basically these are there's a library of these. It certainly covers everything you would ever want to. And then every now and then somebody says, how do you do this? And then we'll figure it out or something like that, right? So, okay, I'll move on. And now I'm going to show you how, if you just put all these things together, they're all very simple, you get something very simple and very short. And that's this. So what you do is you start with a problem in disciplined convex programming form, right? So, I'll show you examples shortly, right? And you have cone representable library functions. So remember, a library is just a set of descriptions of these cone programs, right, that tells you how to do this. And then it turns out it's extremely simple to just automatically and immediately transform to an equivalent cone program. So, okay, so how do you do it? And this entire page tells you everything. So there's actually nothing more than this. This is it, right? So here's what it is. What it is you walk, so you build these parse trees, and then you walk the graph, okay? And what you do is every time you find a non-affine library function appearing in the parse tree, you simply swap in its cone representation like this, and that's a new variable y that you've created, okay? It's that simple, right? That's what you do. And what happens is if you simply do this, and you can do it recursively or whatever, it doesn't matter. And in a modern language, this is basically 2 lines. This is 2 lines because you tell the root to do it, and from the root it spreads down, and it all happens automatically, right? So this just happens, and this yields a cone program. What is always the case is that cone program is a relaxation of the original problem. But it turns out if the DCP rules match, then you know ahead of time before you even solve it that it's actually equivalent, right? So these are the monotonicity rules guarantee that the cone program developed here is equivalent to the original one. So that's the idea. So it is just this, right? So it's weird because if you actually look, I mean, if you look in something like CVX, it's horrible because MATLAB is not a real language and they don't have a real object model and there's piles of stuff in there. But if you look at an implementation in something like Julia or Ruby or something, it looks like that. It's even shorter, right? You just have a method and it's very, very simple. Okay. Okay. Now I'll say a little bit about it in a minute, but let's look at a quick example of how these things look, right? So suppose you wanted to solve this problem. I mean, I have no idea why you would, but you know, I guess that's some kind of lasso type thing and some bound on this. And the way I can tell you how this used to work, right? So the way this used to work was we would be in my office and I would say, yeah, this is how we're going to reconstruct our image using this. And then I'd say that's convex. This is transformable to a QP or something. And then I'd make the graduate students do it. Okay, so I'd say go do it, right? Okay, so that would be the idea. But yeah, actually grad students are not that reliable, so it's not that good a method anyway. So, but CVX, probably most of you have seen this, but this would look something, you'd write this. You'd write in MATLAB, CVX begin. Variable x of n, that's a constructor to create a variable x. And then you would simply write something like this. By the way, the keyword subject to here does absolutely nothing. It's just to make the source code look like the LaTeX, right? That's all it is, right? So, and then everything is parsed here, and it all automatically. And what will happen is when you get to this end, when you get here, what will happen is this is compiled into a semi-definite program, right? And then it's solved by any of several solvers, right? So that's the idea. Actually, it's quite hilarious because sometimes if you solve a least squares problem, that's the oldest convex problem there is. It's the simplest, right? It's sort of developed by Gauss. It's the simplest thing there is. It's got an analytical solution by solving linear equations. In CVX, if you do a least squares problem, it introduces all sorts of new variables, and then generates a semi-definite program, right? Then it fires up a primal dual homogeneous embedded interior point solver. This is to solve a least squares problem. So this sounds idiotic, and actually, amazingly, the inefficiency is not much. It's like 5 to 1, and it's no more, which is crazy. That has to do with sparsity, but okay. Okay, so what are some functions? There's all the functions we've talked about, which no one really ever uses. I mean, mostly, right? But they're there just to kind of show off or something. Although it's weird, every now and then people start using some of these things, and that happens. So, okay. More recently, we're moving over to things in real languages like Python. And so there's CVXPY, was developed by Stephen Diamond. He's the same one who developed I did with him, but the visualization, the parse tree stuff, right? So actually when he did this, he was an undergraduate. So in pure math and computer science. So so there's an undergraduate, I worked with him, and he developed this. It's in Python, and it targets a lot of cone solvers, but it would look something like this. And if you know an object-oriented language, then this will look extremely familiar, right? So this is a constructor. It creates a variable object, Interestingly, in these more advanced languages, unlike CVX in MATLAB, variables live a complete separate life outside of problems. So they can be shared across problems, and they are objects on their own. So here you create an object. Then this creates, everything's been overloaded here. This function sum squares. This returns an expression, a CVXPY expression. That plus is overloaded. So that's an expression. An objective, well, you say minimize a cost, and it returns, the other keyword here would be maximize, of course. That's an objective. And then a constraint is, this is a list. I mean, again, if you read this, it's clear. That's a list, and that's a constraint. And so that's a list of constraints. And then this creates a problem object. That's a constructor for a problem, and you call it with the objective and the constraints. It constructs a problem which is not solved or anything yet. To solve it, you call the solve method on it. And that has the side effect of writing onto all the variables in the problem, right? So if you wanted to get x, the optimal x, you would write this. So again, if you program in a real language, this should look, in a real and relatively modern language, this should look very familiar and natural. So okay. So when you do this, not only is the code much shorter. I mean, the base is 50 lines, but what happens is you get all sorts of other cool stuff. You can do things like add a parameter in. And in a parameter, what it means in a parameter is you don't have to reparse the problem. You can solve multiple instances of the problem with you just change the parameters. And so here again, if you know Python, this is very clear. This says make an empty array of values, and then it says for all the values in 100 values logarithmically spaced between 10 to the minus 4 and 10 to the 2, it says assign gamma to the value, and then solve the problem, and then append the value, right? So it's this is a simple thing, but what this does is this does not reparse, right? So for example, in something like CVX, it would reparse the entire thing, for each lambda as if it were completely new. So, okay. And I think I'll skip over this and just go to the conclusions. So the idea is that disciplined convex programming is a formalization of the mathematical idea of constructive convex analysis, right? So, and it's a simple method to certify that a problem is convex. And then it's used in several domain-specific languages for convex programming right now. And what these do is they make rapid prototyping very easy, right? So it means that I can rapidly I can solve modest-sized problems. I can code immediately, like in minutes, right? I can have something up and running, and so that's actually been this I did not really appreciate how much this means. It turns out that there's a lot of people who don't need to know and don't want to know the details of how it's done. They just want to see it done. And so it turns out that, and the result is that a lot of people use these things who don't know how any of it works, and why should they? So, okay, so I'll finish just by saying happy birthday.
We were ahead of time when you started, and we're still. That's good. That's just perfect. We have time for questions.
Yeah.
Stephen, and a few words about solvers. Which solvers are available here?
So for these things, actually all of them are completely separated from solvers. So there's a system like CVX, CVXPY, Convex.jl, and then they're completely separate from the solver, right? So you can use any solvers. The solvers we use in the MATLAB are things like Sedumi and SDPT3. And maybe that's about it. There's commercial ones, which are quite good, in fact, like Mosaic is quite good. And then for one of the things we insisted on was for CVXPY, was that just for moral reasons, it should be open source from the beginning to the end, right? There should be not one piece of anything not open source in it, right? So for example, for CVXPY, we ended up just building solvers, our own solvers, to make sure that they were completely open source. So we built something called ECOS. It's a primal dual homogeneous embedded interior point method, completely standard. It's 750 lines of C. That's a very small number. That includes everything. It has no libraries, so that uses no numerical libraries. It's single thread, obviously. So that's one ecos. And for a small problem, I mean, it's just a second order cone solver. It's fine. We also built recently, I was talking to a few people about it, something called SCS, which is it's a first order method, but it'll scale to problems with 1 billion or 10 billion variables. I mean, that's not going to run on a laptop, right? Definitely not this one. But that one will run on a real machine, you know, like a 32-core machine with half a terabyte of RAM. So these are all of it. Everything's open source. Not only are they open source, but actually now most of these things are developed in GitHub. So do you know about this? Oh, it's great. Don't people know about this? GitHub? Okay, all right. So yeah, so good. Actually, there's this new trend is that actually you do all of your development, even at companies, and everything you do is completely open to the entire world. Absolutely everything, right? So source code, everything. You can see like how many mistakes, what you checked in, how many times you've checked things in, and other people will read your code, suggest changes, say you got a mistake, this is wrong, here's this thing, or I just extended your code. So this is all, that's how we do all of this now. Everything is online and free and clear, so everyone uses that. We have a GPU-based one we've now done just for fun, which was just our way to start doing that. And that's great. So, but we're hoping actually other people will get in and start adding solvers. If you make a solver, it would be silly not to make it compatible with these systems, because if you make it compatible with a system like any of these, it means immediately you can test it across 10,000 problems from 50 different fields. So if you want to test a solver, if all you want is one plot to put in a paper, okay, fine. But if you actually want to make a solver that works across a lot of things, you just make it's actually very simple to make the interface, and then this will do it. What we don't have yet is an organized way to actually do the testing. We want to do that. So the idea is maybe I'll get an undergrad to do this. And then if you make a cone solver, you just take, we'll make it, if you compile it with the right things, then we'll immediately be able to test it across 10,000 problems from 50 different fields. We'll do control, signal processing, image processing, networking, circuit design, mechanical engineering. We'll do all of it. And then you'll know, probably the next morning, because it's going to take a while, the next morning you'll find out how reliable you were and how your timing was compared to other things. So anyway, that was a long answer about solvers.
Interesting answer. More questions?
Yeah.
In your code representation, this XY belongs to the code.
Yes.
Which code?
So I didn't say, I should have said. Actually, the truth is this is completely generic, right? So what I should have said is that this is a direct Cartesian product of cones. And of course, what it is in the end, your solver has to be able to handle this cone, right?
But it's not clear how to code it.
Oh, no, it's completely clear. What do you mean? Yeah.
How to write in the problem statement for map?
Oh, no, it's very, very simple. No, it's extremely simple. This is a talk, so I don't have all the details here, right? Not to mention it's a 30-minute talk. But so this thing is a Cartesian product. And in fact, these things, they're very, very simple. It's just, you can handle, well, I tell you exactly what it is. Here are the things that solvers handle right now. They handle, this is either the free cone, so it's R, or it's the zero cone, that's the dual, so that's just the element 0. It's R plus, right? It's second order cone, right? It's the Lorentz cone. It's the semi-definite cone, and the exponential cone. So actually, for people here, it turns out people who write interior point things avoid the exponential cone because it's not self-dual, and so that makes some of the math look not pretty. But if you do exponential cone, then you can handle essentially 99% of all convex problems that arise, right? So anyway, so that's what K is. It is actually nothing more than what I just said. And the idea is if you want to do problems where there's some fancy cone, we simply put it into a higher dimensional space and reduce it to these small ones. So does that answer your question?
Okay.
Yeah.
Correct your
expansion code is self-dual.
What's that? It's not self-dual. No, it's not. No, you have to switch. You have to switch two arguments, and then it's self-dual. It's not. Yeah, it's very close. The dual is the same thing, but you have to apply. You have to permute two entries. So, yeah. I mean, I think so.
Any other questions?
Yeah.
And did you consider the problem of optimal tree representation of functions?
Optimal what?
Optimal tree representation of functions in previous part of your representation.
No. No, but I know people who have. Yeah. So the question was, so once you actually are doing everything at the level of expression trees, you can do what people who make compilers do. In fact, we're doing something close to what people who make compilers do. So the way to think of what a compiler does is I take your source statement in some language and I keep transforming it. But I have to be able to prove that at each step it's equivalent, right? So for example, when I'm making a compiler, I could rearrange operations because I know it's going to work. Of course, that's kind of what we do. But no, we haven't really done any. That's code optimization. Nope, no one's done any.
Any other questions? I guess we'll maybe have
Yeah,
other questions.
I'm
in
around,
3
so,
days,
yeah.
so
Good.
Thank you again.
Okay, thank you. And happy birthday.